Hello, we are from ChemPraxis, and in today's video, we will be covering Physics Paper 3, Variant 8, May-June 2025, Question 1. In this experiment, we will be investigating the properties of a pendulum. Now, as you can see, we have a diagram here that we need to set up accordingly using the apparatus given to us. So these are the apparatus that are provided for us for the setup. As you can see, we have a stand, two bosses, the pendulum bob with a string attached to it, two rods, one with a hole through it and one without, and a meter ruler. Now, let's assemble the apparatus according to the diagram. Okay, so now that we have set up the apparatus, let's proceed on. So there's another diagram here, where we'll need to thread the string of the pendulum up through the hole in the upper rod and pull it through until the pendulum bob is approximately 2 cm above the bench. Then we'll need to use a clip to fasten the string to the stand to prevent the string from slipping down the hole. As we can see from the diagram, this will be an oscillation experiment. So now let's just follow through the instructions and set up the apparatus. So after setting up the pendulum, we will also need to turn the lower rod horizontally so that the string just touches the rod. So now we will need to measure L1, which is the distance between the center of the bob to the bottom of the upper rod, and L2, which is the distance between the center of the bob to the bottom of the lower rod, using the meter ruler provided for us, which I have measured to be 49.0 cm and 16.0 cm. It is important to remember that for each reading, it must be recorded to the smallest division of the measuring equipment. As we are using a meter ruler, which can record to the nearest millimeter, which is 0.1 cm, hence, we'll need to write the measurements to the nearest 1 decimal place. Moving on, now we will need to push the bob a short distance away from the lower rod, then release it to cause it to oscillate, which then we will need to find the period t of the oscillations. For every oscillation question, always remember that it is compulsory to find 2 readings of the time taken for 5 or more oscillations, as it is more accurate compared to just taking the time taken for 1 complete oscillation. In this experiment, I will be measuring the time taken for 10 complete oscillations. Keep in mind that if your other oscillation experiments are unable to complete 10 full oscillations, you can always adjust and take the minimum of 5 complete oscillations. Alright, let's move on to take the measurements. So we have our stopwatch here with us, and following the instructions given, we will push the bob slightly away from the lower rod and release it while pressing the stopwatch simultaneously to start the measurement. At the 10th complete oscillation, stop the stopwatch and take your reading. Make sure that you are recording the time taken to 2 decimal places, as it is the smallest unit that the stopwatch can measure. So after repeating the experiment for the second time, we now can find the period t of the oscillation. First, we will need to find the average time taken for 10 complete oscillations. Then, we can directly use the average time taken and divide it by 10 to find the time taken for 1 complete oscillation, which is our period t of 1.122 seconds. Let's move on. Now, we will need to move the string through the hole and refasten it to change L1, and we will need 6 sets of values of L1, L2, and T. Below right here is the table that I have drawn with all the data collected. Keep in mind that although they have not mentioned anything about including T1, T2, and average of T, you would still need to include them, as it shows the examiner that you have a clear working to get your period T. So how do I set for our L1 and L2 heights? First, we will need to set the maximum and minimum value of our L2, as it is the only factor that is limiting our oscillation. As we can see here, if we set our minimum value of L2 too small, the pendulum bob would hit the lower rod, which would not be a proper oscillation. And if the maximum value of L2 is too large, the pendulum bob would hit the bench during oscillation. So we will need to set the range for L2 just right so that it can have the maximum range while performing the proper oscillation. In this case, I have chosen the minimum of L2 to be 5 cm, which is here, while the maximum of L2 to be 17 cm, right here. So now that we have our maximum and minimum values of L2, we can easily set the values of L2 in between as long as they have regular intervals. For our L1, since we know that the distance between the lower and the upper rod is 33 cm, we can directly add the L2 to 33 cm to get L1. Now let's talk about the number of significant figures of your readings. Remember, for any calculated values from raw measurements, always follow the smallest significant figure of your raw value or one significant figure higher than your raw value with the smallest significant figure. Let's say for your average t and period t, you can follow the significant figure of your t1 and t2, which is for significant figure. And for your cert L1 plus cert L2, since they already have mentioned to measure them and round them up to 3 significant figures, you can follow just that. Let's move on. Now we will need to plot a graph of t on the y-axis against cert L1 plus cert L2 on the x-axis and draw the line of best fit to find our gradient and y-intercept. So this is my graph. As you can see, all the points are as close as possible to my line of best fit, and at least 50% of my grid is being used. Always make sure to label every 2 cm, which is one big box, on your scaling, and the intervals of the scaling are regular. For example, you can use +1, +2, +5, +10, so on and so forth, as long as it is easy for you to calculate with your scaling. And always remember, for physics graph, you will not need to start from 0. Adjust your scaling and starting point so that you use 50% or more of your graph. Now, we will need to proceed to find gradient and the y-intercept. We will use the rise over run method, which is drawing a triangle between the two coordinates picked. Always pick the points that your line of best fit perfectly passes through, and always try to use the widest range of coordinates in your line of best fit. Now that we have our coordinates, let's proceed with the calculations. For the gradient, we can just use y1 minus y2 over x1 minus x2 method to find, and for the y-intercept, since our graph is not starting from the origin, we will need to use y equals to mx plus c method, as we could not see the y-intercept directly. For the calculated values, you can do 3 or more significant figures. Always remember to include your units. Moving on to question D. It is suggested that the quantities of t, L1 and L2 are related by this equation, where a and b are constants, and using our answer in C3, we will need to determine the values of a and b. If you look at this equation, we will notice that this equation will overlap with our y equals to mx plus c. Hence, we will know that a is our gradient and b is our y-intercept. So now we will just need to mention that a equals to gradient and b equals to y-intercept, then we can directly write our final answer. Just remember to take note and write your units. Moving on to question E, theory suggests that a is related to the acceleration of freefall g by this equation. Using our values of a, we can calculate a value for g. So after substituting our a into this equation, we'll get 1081 cm seconds to the power of -2. So this is the end of the question. If you like the video, don't forget to like, share and hit that subscribe button. This is ChemPraxis and thanks for watching.